Arithmetic sequences. So this is our second lesson with arithmetic sequences, and it says there are many types of sequences, but there is one that is related to linear functions, and that's our arithmetic sequence. Those two go hand in hand. In fact, it is a type of a discrete linear function, and we'll talk about that in just a second when we look at exercise 1. These are known as arithmetic sequences. So if you remember back from lesson 12, we talked about the introduction to arithmetic sequences, and the definition of it was that the numbers in the list are whole numbers. There are counting numbers. So that's going to lend itself to what we're going to talk about right now. So it says, Evan is saving, I have a little typo, to buy a new toy. She already has $12 in her account. She gets an allowance of $4 per week and plans to save $3 in her savings account. So she must be spending that dollar on something else. So it says, fill out the table below for the amount of money Evan has after n weeks. So here's our weeks. And the A of n, or our output, is going to be our money. So at week 1, she has $15, because remember what it says. She started with $12 in there, and then at the end of the week, she gets her allowance and puts 3 more in there. So let's sort of back this idea up. So at week 1, she has $15. So if I were to backtrack here, what would be week 0? Think about that for a second. At week 0, she would have, what was her starting amount? She would have $12, correct? Okay, so that is, think about that. At week 0, she'd have $12. It's her beginning amount. That's our y-intercept. And then we start to add $3 after each week. So we say, okay, plus 3. We can continue on. Plus 3. Plus 3. You guys got this, okay? All the way to week 7. And then it says, write a recursive definition for the sequence. So recursive definition, let's revisit what that means from lesson 12. Recursive definition, you must have the first term, and it depends on the term before. Okay. Depends on the term before. That's key in this problem, okay, or recursion. So what is our first term? So our A of 1, what was our A of 1? Okay, our A of 1 was 15. And then how did we generate terms from that? Okay, we would say to get any term in line, we would say we'd have to take the term before. Whoops. The term before. So remember that A of n minus 1, that just indicates the term before. And what did we do to generate these terms as we moved down the list? What were we consistently doing to the term before? We were adding 3 to it. Okay? So you need the first term, and then you need the formula. And the formula says to generate any term, say A of n, that's equal to take the term before and add 3 to it. There's our recursive definition. Part C says, what's wrong with this graph? So something is wrong with this graph. I see the points plotted, and they all look good, and I see that they have connected the dots. Well, this means that this is continuous. Is there ever a point that Evan has $16 in her savings account? Or does Evan ever have $20 in her savings account? Or $25, $26? Remember, this is only indicating 15, 18, 21. It's increasing by $3 each month. So this would indicate that she could have any amount in her savings account, starting with the $15 and all the way up to the $33. So it's incorrect because we have it's called a discrete function. we have a discrete function. We have, let's see, hang on, let me pause for a second. She puts money in once a week. Okay, here's some more reasoning behind it. Okay. Once a week. Okay, she doesn't put it in the middle of the week, okay, at the end of each week. This right here, when we connect, that would be considered a continuous function. Okay. Arithmetic sequence is a discrete function. So Evan proposes the following explicit formula. Okay, so that's something new. Okay, we have a recursive formula, a recursive definition right here. And now we have an explicit formula. And just hold that thought for a second. For the amount of savings A as a function of the number of weeks N, is this formula correct? Test it. So this right here is an example of an explicit formula. Well, this should look familiar to you. Okay, it's just representing a linear function here, nothing funky about it, in function notation. So they're saying, is it correct? And they said, test it. Well, let's test week 1. So at A of 1, that's 3 times 1 plus 15. So 3 times 1 plus 15 would indicate that at week 1, she had $18. Did she have $18 at week 1? No way. She had $15 at week 1. Okay, so this formula is incorrect. Arithmetic sequences are ones where the terms in the list increase or decrease by the same amount. Okay, that's our rate of change. Given a unit increase in the index where the number is in line. Okay, remember we talked about that in our last video. I want you to do exercise 2. Arithmetic sequences are relatively easy to spot and to sort of fill some spots in line. For each of the following sequences, determine if it is arithmetic based on the information given. If it is arithmetic, fill in the missing blank. If it is not, show why. So let's look at letter A together. I'm going from 5 to 9. That's an increase of adding 4. That's adding 4. These two would be adding 4. So then what would we fill in here? We'd fill in 17. Then in part B, let's see what's happening here. We're adding 5, but then all of a sudden we're adding 10, and then we're adding 20. And then we have this 160 here. Are we adding a constant amount? We're not. Okay, so this is not an arithmetic sequence. It's not arithmetic because the first two differences are not equal. Okay? We have 5, and then we have 10, and then we have 20. We're not adding a consistent amount. You may notice a pattern in here, but it's not a pattern of consistently adding an amount. That's what makes it arithmetic, that adding that common difference. Okay? All right. That's a little foreshadowing to what we'll see later on. You guys are going to do C and D. Find a specific term in an arithmetic sequence without listing them sometimes can be a challenge, but not if you take your time and think about it, okay? So it says, consider an arithmetic sequence whose first 3 terms are 4, 14, 24. What is the 4th term? So if we have 4, 14, 24, and they're telling us it's an arithmetic sequence, so what's happening here? We're adding 10. There's my common difference. So then my 4th term in line is going to be 34. And it says, how many times was 10 added to 4 to get to the 4th term? Let's read that again. It says, how many times was 10 added to 4 to get to the 4th term? And hopefully you see down below, we have added 10 3 times. Right? We added 10 3 times. Okay? So that's our little diagram that we can show. So there's no mistake in why that happened. So let's keep moving. It says, use what you learned in Part A to find the value of a sub 10, the 10th term. Remember, this is just subscript notation. We're looking for the 10th term. It also could be written in our function notation, a of 10. So let's take that idea. So how many times are we going to add 10 to 4? Think about that. Back here, we added 10 3 times to get to the 4th term. So if we want to get to the 10th term, how many times are we going to add 10 to 4? And hopefully you're saying 9. We've got to add it 9 times, which is absolutely correct. So then our 10th term is going to be 94. Let's use a little notation there. We'll use subscript 94. Write a recursive formula for a sub n based on the term number n. Recursive, remember, the term before. So we always have to start out with the first term. We know that that's 4. And how are we generating any term in line? Take the term before. Remember, a sub n minus 1. N minus 1 always indicates the term before. And what are we doing to that? We are adding 10 to it. Now, an explicit formula for a sub n relies on, it's just our nice little linear formula. So if we sit and think about that for just a moment, we say a sub n is equal to the first term plus 10 times, oh, look at this, n minus 1. Remember, how many times, think back to Part A and Part B. What did we do? We had the first term and we added 10 3 times to get to the 4th term. We took the first term and we added 10 9 times to get to the 10th term. So now, to get to any number term, we take 4 and we add 10 to n minus 1. Okay, 9 is n minus 1. 3 was our n minus 1. So if I take and I simplify that, if I distribute, I've got 4 plus 10n minus 10, and I combine some like terms here, I end up with 10n minus 6. So that 10n minus 6, where is that minus 6 coming from? Think about that, my friends. Go back up here to Part A. This is the big piece right here. This is my first term. If I were to back this up and go back to the 0 term, shall we say, I would have to subtract 10. So if I subtract 10 from 4, I'm at, sorry about that, that keeps popping up, minus 6. My friends, that is the y-intercept. Okay, we sit and think about that. All right, the y-intercept. So my output is negative 6. My input is 0. The 0 spot in line. It's not the first term. Okay, it's that 0 spot in line. So that's where that minus 6 comes from. All right, we will work on exercise 5 together. If you'd like to give that a shot, you absolutely can. Come to class and show me how you did with that.